In a previous presentation, I concluded that a system's transfer function can be formulated as a sum of contributions from its different modes. In this presentation, I will continue the discussion on system characteristic functions. So, the key concepts we will meet in this presentation is system transfer functions and also a new concept, the system's impulse response function. But we will start with a more fundamental question. Is our mission in experimental modal analysis possible? Well, from a previous presentation, we know that the system transfer function can be written in this form, where we have a sum of contribution from the different modes. And in the nominators here, we have the elements of the mode shapes, and in the denominators we have the system poles. So in this form, the system transfer function is expressed explicitly in the mode parameters of the system. So in experimental modal analysis, we want to determine the system poles and mode shapes from a measured frequency response functions. And as we know, the frequency response function is the transfer function, the system transfer function, evaluated on the positive imaginary axis. So from a measurement of the frequency response function, can we extract the system poles, the complex valued system poles, and the mode shape vectors? That's the fundamental question. Is this possible? Yes, it is. And the reason is that from the theory of complex analysis, we know that if we have an analytic function that is known in a specific region, then we can extend this function to wider regions by something called analytic continuation. And in our case, we have measured the frequency response function, the red curve here. Well, the red curve here is the absolute value, but we have in principle measured the complex frequency response function. So if this function now is analytic, then we can extend the validity of this function to the whole complex S-domain, except for the singularity poles, the poles. So this theorem then shows that from a measured, known frequency response function, we can reconstruct the system transfer function, except for the singular points. So it will be valuable later on to reformulate the system transfer function to different forms, different but equivalent forms. We have already seen the explicit form, where we express the transfer function explicitly in the mode parameters, the mode shape vectors and the system poles. We can also formulate something that is called a residue pole form. And to do this, we use a Laurent series expansion and formulate it in this equivalent way. So here you can see we have the contribution from the first mode containing the system pole for the first mode, and so on. And then we have something called the residue of the mode in the denominator. We can also, if we combine the contributions on a common ratio, we can get the complex rational form, which can be formulated like this. So we have a denominator polynomial, where A, of course, is dependent then on the system poles, and the nominator polynomial, where the B coefficients is dependent on the zeros of the transfer function. So the denominator polynomial gives us the system poles. It's actually the roots of the denominator polynomial, whereas the nominator polynomial will give us the system zeros, which is, well, from which we can reconstruct the residues, and from the residues we can later on reconstruct the mode-shaped vectors. Another alternative is, in fact, to use the time domain version of the system transfer function, and that is called the impulse response function of the system. So the impulse response function, well, a physical realization of this is what we measure if we consider a system and excite this with an impulse force, using, for instance, a hammer. The vibration response of this system when we excite it with a hammer impact, that is the realization of the impulse response function. In this case, we see a plate that is excited, well, the response of a plate excited with a hammer, and this is actually the acceleration response. So here is before the impact, so we have zero response, and then at this moment the plate is excited by a hammer blow, and then this decaying, exponentially decaying vibration or acceleration is the acceleration impulse response function. And you can see here there's a low amplitude, low frequency vibration that remains for quite a while here, and that is in fact the rigid body vibration of the plate. So the inverse transform of the system's transfer function, that is actually one method to calculate the impulse response function. You can actually define the impulse response function as the inverse Laplace transform of the transfer function. So if we do this and start from the residue pole form, this form, then we can show that the inverse transform of this is this expression. So we have here the contribution to the impulse response function from the first mode, from the second mode, and so on. And as you can see, this is actually, each modal contribution here is a sum of two complex conjugates. And that means then that we can combine these and get 2 times the real part. So this is then 2 times the real part of this is the contribution from the first mode, and 2 times the real part of this is the contribution from the second mode, and so on. So this, as you see here, since the exponent here is complex valued, this is a complex exponential function, which shows this exponentially decaying oscillation. Exactly as we saw in this physical realization of the impulse response function. So, in experimental modal analysis, our mission is to find modal model from measured system properties. And we can, of course, use both frequency response functions, and by analytic continuation we can find the system transfer function. And we can, of course, also use the equivalent impulse response functions, because they contain actually exactly the same information. But in the frequency response function, we work in the frequency domain, and impulse response functions will work in the time domain.